So last week we introduced the sequence and series. For sequence, we use this en. Sometimes we use the starting and ending index. We can list all the entries, A1, A2, A3. Sometimes at 1, we miss at 0. We can start at any number for a sequence. Okay, then we study the series. This is the summation notation. It means we add A1. Okay, so then since we are adding infinite many terms, where we want to check is it convergent or divergent. To do this, we introduce the partial sum. The first k terms, we add them. And then this introduces a sequence, the sequence of partial sums. If this sequence converges, then we see the series also converges, and it converges to yes. So here it converges. Sometimes it's not easy to determine whether it's convergent or not. We have this test of divergence. This gives us a sufficient condition when the series is divergent. If the limit of the entries is not 0, if it is not 0, it must be divergent. So some example we can check. This one is 1 minus 1 plus 1. This one can see the entry. If we take the limit doesn't exist. In particular, it's not 0. Therefore, this series is divergent. Okay. That's how we apply this test for divergence. Okay. But sometimes this test is not good enough. It cannot tell if the series is convergent or divergent. We have this series. This one we know the limit is 0. But we also checked it's divergent. One. So that's the point for this test for divergence. It tells us if the limit is not 0, must be divergent. But when the limit is 0, maybe convergent, maybe divergent. This test is inconclusive for situation like this. Okay, now let's recall how we verify this is divergent. We introduce another test. It's called the integral test. Yes. The integral test, if the entry is the value of a function at n with positive and decreasing, then the series and the integral they either converge or diverge at the same time. So we use this symbol. That means the two sides, if this one is convergent, this is also convergent. This one is divergent, it's also divergent. They converge or diverge simultaneously. So sometimes this integral is easy to compute. Then we can determine whether this is convergent or divergent. Here, the point is, it doesn't mean they are equal. Yeah. Who is it? Okay. 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 So an example showing the difference is the 1 over n squared. By the integral test, we want to check this we checked is convergent and equals 1. So it implies okay. But this test does not tell us what this it converges to. Okay. To find this number, why? Okay. 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 To actually find this number in something in Fourier series. Maybe we mentioned this name before. This number is okay, Zizhen, how do you see this name? Sakina. Okay. because he's a French. Fourier. Yes, so yeah, American, many people say Fourier, but if he's American, it would be Fourier. But he's a French, so it's maybe different. Some do you speak French? And you, Sophia and Elisa?
Yeah.
Okay, Sophia, is that correct? Fourier.
Yeah, it's close.
Okay, it's close. Okay. 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 Uh, so this is about the integral test. Next, we will go a little bit further. We can consider this alternating series. Okay. A typical example is the alternating harmonic series. Okay, Zichen, what's the first entry for this series? Sakina, second entry. N equals 2, what do you have? Negative 1/2. Sophia, third entry.
Um, 1/3.
1/3. And Elisa, fourth entry.
-1/4.
Constant continuous. This is close related to the previous one. So this one is called harmonic series. We know it's divergent. This one has called alternating harmonic. Okay, the harmonic series is divergent by the integral test. What about this one? How do we determine if it's convergent or divergent? This one, if let's see, if we add these two, what do you have? 1/2. Add this two is 1/12. If we add them, we add a smaller and smaller number, the difference. So this will be n is odd, 2k plus 1 minus 2k. Maybe minus 1 is better. This goes to, if we simplify these two terms, okay. So if we group the neighboring two terms, it's like we're adding this series sequence. This one will be convergent. Okay. So it is convergent. So, but for this alternating series, we have a new test. alternating. Let's see sigma. Here we assume Bn is positive. Now if Bn decrease to 0, okay, so you can see the difference between this and the previous one. If we are dealing with the alternating series, in this case, if the sequence is decreasing and go to 0, it must be convergent. This is very different from the divergence test. If we have the positive series, compare. This one divergent, this one convergent. The structure over here have an extra sign, change the positive, negative, back and forth. This gives us stronger convergence properties. A similar one. Okay, two more series. First one, summation 1 over the square root of n. Second one, change signs. Okay, for this one, how do we determine if it's convergent or not? Sophia, what would you do? What method could we use for this one?
You take the limit?
If we take a limit, we get a 0. Does it tell us something? Do you mean the limit of the entries or the limit of the partial sum?
Uh,
So for this one, could we apply the integral test? What function would we pick if we want to apply the integral test?
over square root of x.
If we apply this, the integral. Okay, this one, convergence or divergence? The integral. So we find the antiderivative. This is x and the derivative will be x 1/2. If we take a derivative, give us 1/2 should be twice of this. This one goes to infinity. So by the integral test, is divergent. So the first one, it is divergent. Now the second one is essentially the same, but with the sign. Now we should apply our alternating series test. The limit is 0. So by the alternating series test, I'm going to use AST for short. So it's alternating series test. AST. So here we have this two different phenomena. So a series. If we take absolute value, okay, this applies to our alternating harmonic series. Also applies our new series. So we want to distinguish them from the following. For this two, the series itself is convergent. But if you take absolute value, it's divergent by the integral test. But this one, it is convergent. With the absolute value, convergent again. So both of them are convergent. Maybe all three of them are convergent. However, this one is stronger in the sense that if we take absolute value, it's still convergent. So this one, we will call it absolutely convergent, because if we take absolute value, it's still convergent. A new term. Okay, so it means if we take the absolute value of this series, it's still convergent. Unlike the previous one. Previous one, if we take absolute value, go to divergent. We call it conditionally convergent. The difference between this is very subtle. Zichen and Sakina. Let's go back to this conditional convergence. Why it's different? So when we do addition and subtraction, we know it's commutative. If we change this we add 1, subtract 5, or subtract 5, add 1, it's the same. But if we are in this region, the order matters. If you change the order, you get a different number. Do you believe me? Here I say, if let's see, in principle, if I add 5, number 3, vs minus 3 add 5, I claim in this case, if it's a conditional convergent, the order matters. If I change the order, I will get a different number. Sophia, you get what I'm saying?
Yeah.
And why? Why? Let's see the, the example. 1 minus 1/2. This one, we know it's convergent. It converges to some number. We use this letter gamma, a Greek letter gamma. Now I'm going to make some changes. I want it to go to bigger than 100. No matter how large a number you give me, I can make arrangement so that this converges to your number, maybe even bigger. In the same way, if you give me any number, I can rearrange to something bigger. Give me any smaller number, I can rearrange so that is to something smaller. Convert it to something bigger than m. So how do I do this? How could I make the sum arbitrarily large? How could I make the sum arbitrarily small? It's the same series. The point is if we consider the positive sequence, the point, positive ones, 1, 1, 3, 1/5, and negative ones, 1/2, 1/4, 6. The point is both are divergent. This one diverges to positive infinity. This one diverges to negative infinity. If I want a large number, I will pick enough positive term, add 1 negative term, another positive term bigger than 1, add a small negative number. So we have more than what we need since this will go to infinity. Okay, okay, this is a very interesting fact, but maybe not. You are not. Do you know? Okay, okay. What's the purpose of my argument here, Zichen? No. So this one, by our test, we claim it's convergent. However, so this convergence in this order, we minus, subtract, add, subtract, and subtract. And if we do it in this order, we get one number. The same manipulations, but if we do it in a different order, I can make it arbitrarily large. If I do it in a third different order, I can make it arbitrarily small. So this maybe it's about 1. I can make it them go to bigger than 100. I can make them go to 100 million. And why is that? I can make another one can. He can rearrange the order so that the less than 100, negative 100 million. How is this possible? It's the same numbers. How could we make it arbitrarily large? How could we make it arbitrarily small? So this is the mathematics about infinite. Infinite in many terms, adding to infinite. Infinite in many terms, adding to negative infinite. Now, if we pick a large chunk of positive ones, then we go with a smaller one, a negative one. Then another long chunk of positive ones, then a smaller one, negative one. Another long chunk of that, smaller one. In this way, it can be arbitrarily large. Or I can go a lot of negative ones. I add one small one, still very negative. I add another chunk of negative numbers. Because it goes to negative infinity, we will never exhaust this. Add one small positive, a long chunk of negative, one small positive. In this way, it's the same collection, but it can be arbitrarily small. Elisa, you hear me? What do you think?
Oh, kind of makes sense.
Okay, so the point is this part. This is divergent. I can pick a chunk. Let's say I pick something because it go to infinity. It will be bigger than 100 at some time. Then I make a stop. I put one negative number. Because to go to infinity, the remainder also go to infinity. I can make it another 100. Then I add the negative number. Another 100, add a negative number. Another 100, a negative number. So eventually this will go to infinity. Okay, so there's something you pay attention to when we deal with finitely many sums. If we stop here, the order doesn't matter. I subtract, then I add, or I add, then I subtract, doesn't matter. But if we deal with infinite many terms, the order matters. You change the order, you get different number. Okay, so order matters. Okay, so this is about something. Then we will move to the next one about this ratio and root test. So both of these two tests, we have a model over there. It will be the geometric series. Okay. For this one, we know it is convergent when R is less than 1. And it is divergent R bigger than 1. Now give a general general series. We want to compare this with our model. So we consider the quotient. So this will be the ratio of the next term over the previous term. If this is decreasing, then it will be very close to this one. So Vs Rn plus 1 over Rn, this will be R. So the ratio test if the limit of this ratio equals to R that is less than 1, then it's convergent. If it's bigger than 1, it's divergent. In the special case, when it equals 1, in our case, this test is inconclusive. Okay. Okay, let's try one example. This series, how do we determine it's convergent or divergent? Could we use the integral test? If we try to x squared 2 to the x dx, okay, maybe not, I don't know, not easy. Maybe can be done, but what we do here is let's find the limit of the ratio. Okay, let's find the ratio. This is our an. What's the ratio? So first will be an plus 1. N plus 1, I'm going to replace n by n plus 1. And 1 over an, 1 over n plus 1, 1 over an. I flip the second one, get n. I do some simplification. This goes away and goes away. One half 1 plus 1 over n squared. All right, what is this limit? Sophia, if n goes infinity, what do you get?
1/2.
Get 1/2. Okay, so this is less than 1, then by our ratio test, this is convergent. Okay, try another one. This time, a little bit strange. N factorial. Let me make it not that difficult. I go from n to the cube, 3 to the n. Okay, let's check if it's convergent or divergent. What do we do to check? Find the first, let's simplify the ratio. an plus 1, 1 over an. I'm going to replace n by n plus 1. I get an plus 1, n plus 1. And flip this an. Flip this an will be 3n n cubed. Simplify 1/3. Okay, Zichen, what's this limit? When n goes infinity. One-third. This converges to 1/3. Okay, so then by our ratio test, we know this is convergent. So this ratio test, we compare our series to the model. Another one is very similar. We call it the root test. Sometimes it's not easy to simplify the ratio. We have the following. Take the absolute value, the nth root. If this is less than 1, then we say it is convergent. If it is bigger than 1, divergent. Equals 1, inconclusive. This one. Okay, so this is the same thing we compare with our model. So r to the n, absolute value 1 over n is a bit. Okay, a new series. How do we determine it's convergent or divergent? this term, we can try if we try the ratio test, it's very complicated. Replace n by n plus 1, n by n plus 1, this consider the 1 over an can be done, but complicated. But if we try the root test, what's the nth root of this term? The whole thing can you simplify this nth root? Can you simplify this? Something nth power, absolute value, then the nth root. Okay, because in this case, nth power, the nth root, because this is a positive number, so we can drop the absolute value. What we get is 2n plus 3, 3n plus 5, n times 1 over n. Okay, so okay, now what's the limit when n goes to infinity? N goes bigger and bigger. If it's not easy, I'm going to divide the numerator and denominator by n, see what we get. Divided by n, what's the numerator if we divide by n? Denominator. Then we take a limit, you get. When n goes bigger and bigger, what can I say about this term? This term and the whole term. So this goes to 0, this goes to 0, what do you have? Okay, so 2 over 3. Okay, so it's less than 1, so by our root test is convergent. Okay, so another test. So both this ratio and the root test, we compare them to our model series, this geometric series. If this is less than 1, it's convergent. Bigger than 1, divergent. However, case when it's inconclusive, when it's equals 1. If it's equals 1, this doesn't work. You try different tests. Okay, so that's the preparation for the functions. So we will have 5 minutes break. After the break, we go from series to power series. Okay. Okay, 5 minutes break. So in the previous case, we studied the series. Now we will introduce the variables. We start with the simplest one. From a series to a power series, we let the R change. Now when X changes, each term changes. The summation also changes. We will call this a power series. This is a very special case. We can allow the coefficients. For power series, normally we start from n. So, we start from 0, 0, 0 for power series. An A0, A1. The coefficients. Okay, let's check what they are. So K that's 10. Coefficients and C the center. Okay, the so this will be a function. As a function, the very important step to figure out the domain. The domain when this converges, the domain when the function is defined. So here we call it the interval of convergence. The domains on which the series is convergent. Five minutes, it's not 10 minutes. Okay, so from series to power series. For series, we have a sequence of numbers, we add them, we get a series. But for power series, now we have the variables. Our x may change, x 0.5, x 1/4. Given x, we get a number. X changes, this number changes to give us a function. We call it a power series. This is a special case. I will have the general case. General case will allow the coefficients an, and the center can shift. When shift is by c. For series, we usually set as 1, but for power series, we usually set as 0. Okay, so next, we'll figure out the domain, the definition on which the function is defined. We'll start with this one. From sequence to series. This one, if we do some computation, it will be 1 over r. Okay, using this fact, could you figure out the domain of this function? When will it be convergent? When will it be divergent? Zichen, what do you say? Why use the knowledge over here?
What? Wait, when is it convergent?
Uh-huh. So we can compare it with this one and see when the absolute value of r less than 1 is convergent. So here the same thing when the absolute value of x is less than 1, it's convergent. Okay. So in this case, this domain, we call it the interval of convergence. Next, we'll compare these two functions, the power series, the rational function. What's the difference between them? Sophia, what do you see about these two functions? What's the difference between them? Over here, we see they are the same.
This one is
Let's see, what about the domain? What's the domain of this function?
it excludes one.
Okay, so the domain of this one, and we just studied, the domain of this power series is only the interval. Okay, so can I see the difference between these two? Here we see they are equal. However, this one has a much larger domain. This one has a much smaller domain. They equal on this domain, but if this one is defined as 2, if x equals 2, it's a -1. However, if x equals 2, this one diverges. Even they have the same expression on an interval, but they give us different functions. Okay. A slightly different one. Let me some power series. What's the domain of this function? Interval of convergence. This, we can convert this to something like that by using the power rule. This will be sigma 2x times power. So we just replace x by 2x, we get the formula. And it's on the domain when 2x less than 1. So this is this less than 1/2. So for this series, the interval of convergence another function. How do we find the interval of convergence for this one? this one, let's use this root ratio test. By the ratio test, an I'm going to replace every n by n plus 1. I get an plus 1. I flip this, I get xn. Then I simplify. Simplify. If we take a limit is x. We take absolute value. It converges if this is less than 1. So this power series, the interval of convergence, the interesting thing, maybe the difference between this one and this one happens at the endpoint. Okay, then what happens if x equals 1 for this one? This one, if x equals 1, convergent or divergent? Okay, what test do you use? Okay, there's a test for divergence because this, the limit of this is not 0. Okay, divergent. X is -1. So Kina, what do you say about this series? Convergent or divergent? So let's check with the limit of this sequence. What's the limit when n goes to infinity? Even, 1, odd, -1. 1, -1, 1, -1. What's the limit? Cannot tell because the limit doesn't exist. If the limit don't exist, then this one is also divergent. Okay, divergent. Okay, now we move to this one. We will check the endpoint. Sigma x equals 1. Sophia, this one convergent or divergent?
Ne- neither.
It cannot be neither. It's either convergent or divergent, or I don't know.
It's convergent.
What test do you use?
The ratio.
So this one we use the integral test. We go
Oh,
to logarithm, which implies it's divergent. Okay, the integral test. Divergent. Okay, the other endpoint. Elisa, this series, convergent or divergent? The previous one, divergent. This one is alternating. And all of you. convergent or divergent? This one is alternating. You can apply the alternating series test. This on the denominator, the term go to 0, and it's alternating. So by the alternating series test, convergent. So after checking the two endpoints, we get a better understanding of this power series, the interval of convergence. It converges at the left endpoint, diverges at the right endpoint. Like further change. Sigma. Okay, so previously we used the ratio test to find the interval of convergence, or sometimes we see the radius of convergence. Let's apply the same method to find the interval of convergence of this one. Apply the same method. Okay, let's start work. So we will start with the same expression. So we replace n and n by n plus 1. We get n plus 1. Okay, I'm going to replace this n plus 1 x n plus 1. And I flip this term. I get n squared x, simplify. I take absolute value. I take a limit. Get the what's the limit? When n goes to infinity. The coefficient go to 1. This goes to 1. This stays. Okay, again, the convergence, if it's less than 1, we have the interval of convergence. Next, we check the endpoints. So at 1, we have this series. Convergence or divergence? What test do you apply? Okay, integral test. So by the integral test, we know it is convergent. At the other endpoint, -1, we have convergence or divergence. What test do we apply? This time, if we check the sign, negative, positive, negative, positive, negative, positive. So it's alternating. This alternating, we apply the alternating series test. N go to infinity, so this will go to 0 by the alternating series test. We know it is convergent. Therefore, we can update our interval of convergence. Okay, so now we have three different situations. The initial one on this interval is convergent, Sakina, but it's a divergent at the two endpoints, divergent at the left and the right two endpoints. This one, same interval of convergence, but we checked it's divergent at one point, convergent at the other endpoint. So the interval of convergence becomes this. It includes this one endpoint. The last one, we found the same interval of convergence. However, after we checked the endpoints, we found that they are convergent at both endpoints. So the interval of convergence now includes both endpoints. Okay, three different situations about the endpoints that may include none of them, may include one of them, and may include both. Okay. So given a power series, it defines a function, and we can figure out the domain. Now let's go the other way. Give a function with a domain. Could you find a power series? Okay, so we will start with a special case when C is 0. Suppose we have this. How do we find these coefficients? So this will be A0, A1x. Okay, so how do we find, let's do them one by one. How do we find the A0? Using the function. Did think? So the function is given. Now we want to find a power series for this function. How do we find these coefficients? If we want to find A0, we can just set x to be 0. Then all of this goes away. So A0 will be F0. Do you agree? Why? Okay, why? Oh, God. Okay, perfect. That's all we need. So to find A0, we set x to be 0. So A0 is F0. Okay, now how do we find A1? Sakina. Okay, so the previous we found A0. Okay, we don't need it anymore. I'm going to take a derivative on both sides. If I take a derivative, so F derivative will be this derivative. Okay, let's work. What's the derivative of A0? Okay. 0, okay. And Sophia, if we take a derivative of this term, what do we get?
Negative
Ah, no, sorry. I covered it. Just
Oh,
a
x.
just derivative,
Oh, one.
almost
A1,
a.
A1.
Okay. And Elisa, if I take a derivative of this term, what do I get?
Two
2 into x. And Zichen, third term. If I take a derivative, what do I get? For this one, I get 2a2 squared. So it's a2 times 2x. If it makes it easy, I'm going to rewrite this. And maybe you can figure out 3a3x squared. Okay, now the remaining are the same. Okay, now Sakina, how do I find a1? Okay, very good. That's the key. Okay, Sophia, next one. How do we find a2?
You do
Mm-hmm.
F prime of 1 or 2.
Okay, so that works, but here we have a different way. I'm going to take the second derivative, see what we get. Okay, Sophia, what's the second derivative? So let's ignore this 0. A1, which we take a derivative, what do you get?
Nothing.
Okay, second, what about this one? If we take a derivative, what we get?
2A2.
2a2. And if we take a derivative, what do we get?
6A3x.
That's correct, but I'm going to use 3 factorial a3x. So now I can add one more term since we have too many zeros. This one you can get will be 4, 3, a4x squared. Okay, now with this at the hand, Sophia, how do we find a3? Again, we
Well,
plug in 0.
you take x,
Yes, we subplus this by 0, we get 2a2. From here, we see that a2 is 1/2 the second derivative. So, good. Elisa, how do we find the a3?
one third.
Another derivative. I go to the third. So I'm going to use 3 will be 0 plus 3 factorial a3 plus another derivative will be 4, 3, 2 a4x. So if I set 0, 3 factorial a3. So a3 is okay. How do we find a4? Do you see a pattern over there? From A0, A1, A2, and A3. Could you guess what A4 is? So there will be some derivative. What's the order of the derivative? 4, nice. What's the denominator? 4 factorial. And you can see it from here. 4, 3, 2, 1, 4 factorial. Okay, now let's guess what's A5. Sakina. So, and we have the general case. An will be nth derivative at 0, n factorial. In this way, we get the power series, sigma. And this is called the Maclaurin series. Okay, Maclaurin. Okay, so this is the power series when C is 0. A similar formula holds for general case. And C. It's just a shift, so nothing changes, just a shift. So this is the Taylor series. Could you stay for 50 minutes, Sakina? I want to have one more example if you have time. Okay, one more example. So we have these big formulas. Let's have one simple example. Before I start, I want you to guess if our function is the exponential function. What's the Taylor series? Maclaurin series. Okay, to find the Maclaurin, we need to find the derivative. What's the nth derivative of Taylor series? Fn x. What's this? The exponential function. What's the derivative? Zichen, first derivative. This function. What's the derivative? And the second derivative. So all the derivatives are the same. Okay, if we will evaluate at 0, what do you get? I get 1. So e to the 0 is 1. Now I'm going to apply this formula to this case. So e to the x, the Maclaurin series. Nth derivative at 0, n factorial. I copy the formula, then I plug in. All the derivative at 0 is 1. So the first few terms, when n is 0, e to the x, n is 0 is just 1 plus x. So we get a series for our exponential function. Okay, in the particular case, when x equals 1, what do we have? So e is 1 plus 1 plus 1, this 1, 3 factorial, 4 factorial. So if we add the reciprocals of the factorials, including the zeroth term, we get this Euler number e. Okay, so this is a method. We know what this number, how it's defined, but how do we compute this number? This is a very good method that converted very quickly. Okay, so this is about the power series, and there'll be more. In the future, you will learn more about this. Okay. So we stop here and keep doing the homework. Okay. Don't forget that. And some of the homework may be difficult. Progress is important. You don't have to complete. If you make a good progress, you can also submit it. Okay, guys, any questions? Okay. Bye-bye.
Thank you.
Okay.